Morning, Mackenzie. Morning, Mackenzie.
Good morning.
Way to show up your teacher and be in the Zoom 10 minutes before he was.
Huh?
So way to show up your teacher and be in the Zoom 10 minutes before I was.
I know. The other class I didn't go until the end because it was math. So I like checked in 10 minutes before class was over because I was ahead.
Gotcha. Nice.
But yeah, it's kind of funny. I'm always early for this class, and then math, I only show up if I have to.
Fair enough. All right, what are we doing today? Oh yeah, today we're starting chemistry. Upload the stuffs. Oh goody, I did not bring in things. Just do that real quick. So with starting with chemistry, we're actually going to be starting with the atom and the history of the atom. So go ahead, like I said, make sure you have those notes out. And if my brain can function enough to open the PowerPoint. Say what? I can't hear you. That's fine, don't worry about it. It'll be fine. Because if it crashes, you can still at least hear me. Okay, let's history of the atom. Let me go ahead and remember to share my screen this time. Okay. So this is just kind of a little review over states of matter, but what happens when you put ice in your drink?
It heats it up.
Right, your drink is actually heating the ice cubes. Okay, so it's not cooling your drink is heating the ice cubes and therefore losing heat and becoming more cool. Because remember, you always have to give heat somewhere to go because heat is energy and it wants to move from high to low. So if heat is high in the water and low in the ice cubes, it's going to move into the ice cubes. And what does that do to the atoms in the ice? What is heat for atoms? what's going to cause the atoms to do? You have to speak louder. It will separate them because it's going to cause them to move faster, right? Heat is energy. So if I heat the atoms in the ice cubes, the atoms are going to start to move faster, and eventually they're going to break the bonds that hold them in place, and it's going to melt into a liquid. Okay. All right, now let's start off with the history of the atom. So we're going to be talking about the atom, and we're going to go through the history of the atom because that really shows us a good way to understand the different parts of the atom, how we discovered those parts, what we learned through those discoveries, and how that influences our understanding of the atom in today's sciences, okay? So we have to go all the way back to the Greeks, okay? The Greeks were one of the first groups to really start to talk about the state of the world and try and categorize it and figure out what was going on and why things worked the way they did. And so a Greek by the name of Democritus proposed the first what we call atomic theory. And his theory states that all atoms are small, hard, indivisible, and indestructible particles made of a single material that is just formed into different shapes and sizes. So I like to talk about Democritus as Legos, right? If you've ever stepped on a Lego, you know it's small, hard, indivisible, and indestructible, and it causes immense pain to your foot, right? No. But the key here is that all Legos are made out of the same material, but they're all just in different shapes and sizes. So that's why I talk about Democritus' theory as the Lego idea, because again, small, hard, indestructible, indivisible, formed in different shapes and sizes that make up all of matter. Now, what's important to understand is this is a big deviation from the current understanding at that time of what made things up. So there was another Greek philosopher by the name of Aristotle you may have heard of, kind of a big deal. But Aristotle did not support Democritus' theory. Aristotle was more along the lines of the thinking of that time. And what we need to understand is the Greeks were obsessed with their gods. And so their gods and the elements and things like that, they both basically broke things down into 4 elements. They said everything is made of earth, wind, fire, and water. So they explained living things and people as being made of the earth and given fire by the gods and, allowing them to breathe life and things like that. So they broke things down into earth, wind, fire, and water, the main 4 elements. So Democritus is a pretty big step away from that, a pretty big step into kind of what I would call a more reality-based idea. So again, there's definitely some flaws in this. This was, 460 BC to 370 BC. So a heck of a long time ago. Obviously, he was not entirely correct. But what we'll see here is this laid the foundation for later scientists to come along, pick up on his idea, and expand upon it. So we're going to see Democritus' theory of atomic theory show up again and again as we go through the discussion of the atom. So now we're going to take a giant time leap. If you notice, we're in the BCs here, and now we're already at 1743 AD. So around that time, there was a gentleman by the name of Antony Lavoisier who was born. And as he grew up, he was a pretty big contributor to science. He's known as the father of modern chemistry. It's why we're talking about him today. And he was the first to generate a list of 33 elements in his textbook. He also helped devise the metric system, all right, that wonderful thing that we learned at the very beginning, day 1. Thank you, Lavoisier, for coming to some common sense about how to make measurements and how to convert between units. Too bad the United States is not listening more to Lavoisier. Okay, enough of that. Now, it is important that we go back and give credit where credit was due. History and science and just, again, history in general has not been very kind to women in terms of acknowledging them for their contributions and things like that. But I do think it's important to go back. So we need to understand that Lavoisier did not work alone. He worked very closely with his wife, Marie-Anne Pierret-Palsy, and she assisted him with a lot of his work and ideas. So he was not, working by himself as the man and just making all the decisions as the man. He was actually working a lot with his wife, and she was helping him kind of craft his ideas and things like that. So she needs a good amount of credit as well in all of this wonderfulness. Now, how does he get into the atoms? Well, again, he was the first one to come up with a list of the 33 elements. These are different types of atoms, okay? And he also proposed the law of conservation of mass. Now, we talked about the law of conservation of energy, and that said energy cannot be created or destroyed, only stored or transformed into another type, right? So he's going to kind of borrow a little bit from that idea, but talk more about the matter. The law of conservation of mass, or matter, states, in a chemical reaction, matter is neither created nor destroyed. Now, this is another very, very important thing, because back in that day, some things people just thought appeared. If they didn't see it happen, they just thought, hey, maybe it just came out of thin air, right? This is a big time of not mythology, but like storytelling and urban legend and stuff like that. What you also have to understand is they didn't understand like germs came from places. They thought like maggots and stuff like that would just appear out of thin air. It's an idea called spontaneous generation that didn't hold up very long. But Lavoisier is saying when chemical reactions happen, they don't just appear out of nowhere. They don't make things disappear. Everything's got to come from somewhere. Everything's got to go somewhere. So very similar to that idea of conservation of energy, but the idea of conservation of matter or mass is just in a chemical reaction, matter is neither created nor destroyed. So it's got to come from somewhere and it's got to go somewhere. Now we're going to take a whole lot less jumps in time. So we're going to go from, this around the same time working as Lavoisier was a gentleman by the name of John Dalton. A little bit later, 1766 to 1844. Here is John Dalton and all of his nerdy glory. Now, in 1803, John Dalton kind of is going to update our atomic theory. So he's going to borrow, you're going to see here, he's going to borrow from Democritus, but he's going to kind of add to it the stuff from Lavoisier and just kind of put it together. And then he's just going to slap his name on it and claim it as his own theory. But that's okay. At least he didn't name it after himself. But his theory stated that all substances are made of atoms, and atoms are small particles that cannot be created, divided, or destroyed. Now listen to that. There are parts of both Lavoisier and Democritus in there. All substances are made of atoms. Democritus said all things are made of the same material. And Lavoisier said that atoms cannot be created or destroyed. You can see that in there. Atoms cannot be created or destroyed. So he is borrowing very, very much from his predecessors. And then he's also, again, small particles, okay, kind of, that's going back to, again, Democritus, small materials made into all different shapes and sizes. So Dalton is going to kind of clean this theory up and kind of start to put things together. Now, he went a little bit further and he said atoms of the same element are exactly alike and atoms of different elements are different. And you might go, well, duh, atoms of the same element are going to be the same. That means an oxygen atom is going to be an oxygen atom. It's going to be an oxygen atom. There's not going to be a lot of difference between them. And oxygen is very different than another element, like let's say carbon or silver or gold. Those are all different elements, so they're going to look different. But no one had really kind of come out and defined that. No one really said that. And this is important, that atoms of the same element are exactly alike. What that means is that we can make predictions about chemical reactions just knowing the properties of the element in general, because we don't have to take each element individually. They're not all different. They don't all have their own personality, right? They're all going to act exactly the same. They're all going to work exactly the same. And that's very important, like I said, when you're making predictions about chemical reactions and things like that. He also said that atoms join with other atoms to create new substances. So again, this is kind of getting into Lavoisier's idea that all atoms come from somewhere and go somewhere. So when you take something and you create a new substance from it, it didn't just spontaneously appear out of nowhere. He's saying that atoms are joining together and those atoms are contained in that new substance. So that's, again, borrowing from Lavoisier and kind of building upon his idea. We also have John Dalton to thank for a lot of the atomic weights of the various elements. We have not talked about it too much, and if we were in class, I'd point to that giant table over there in the left of my classroom. But what we need to understand is that he was able to take the weights or masses of a lot of the elements that were known at that time and kind of categorize them. So now we can start to see some more patterns and some more information on the elements that we knew about at that time. All right, so from John Dalton, we're going to jump ahead just a little bit in time to a gentleman by the name of J.J. Thomson. Okay, J.J. Thomson, that he was the first to prove that atoms are not the smallest thing. Up until now, atoms have been the smallest indivisible, indivisible, indestructible particles that are just considered whole. They're the smallest thing. But now J.J. Thomson is actually saying, you know what? The atom is actually not the smallest thing. The atom is actually made up of smaller parts that have their own unique characteristics. Now, how did he discover this? Well, he discovered it while experimenting with a cathode ray tube. I'm going to show you a little video of this, so I'm not going to get into too much explanation. But basically, he had a tube of gas, and what he did was he hooked up electricity to that tube of gas and ran an electrical current through it. And what he saw is it produced a glowing beam. Now, that is true when you heat anything. If you heat anything enough up, it starts to glow. So the gas in there started to emit light. And what he did was he then kind of did a couple experiments with that light to see what would affect it. And what he noticed was that when he took a magnet close to this cathode ray tube, the magnet would cause that band of light to bend. And what he did realize was that part of it would cause it to bend away, part of that magnet would cause it to bend away, and part of it would cause the other side of the magnet would cause that ray to bend towards the magnet. So obviously there was something else in there. Basically, he was able to discover the electron. Okay. He also, actually, before I get into that, so let me take that away. I do want to go ahead and take a look at this video now. So I'm going to go back into the classroom because the link's there a little bit easier to see and use. This is not the right classroom. Too many classrooms. Here we go. All right, cathode ray tube. Let me pause this after this damn ad. All right, I'm going to pause it because I need to mark, and I got to create a new share, and then I also have to share my sound. So there's there, and then share sound. There we go. Okay, let me know if you guys can hear this. If not, it's not too big of an issue, but if you can't hear it, please hop in and let me know. Make sure my sound is up enough so you guys can hear it as well. All right, here we go.
A cathode ray tube is the forerunner of the television tube. It is a glass tube from which most of the air has been evacuated. When the two metal plates are connected to a high voltage source, the negatively charged plate, called the cathode, emits an invisible ray. The cathode ray is drawn to the positively charged plate, called the anode, where it passes through a hole and continues traveling to the other end of the tube. When the ray strikes the specially coated surface, the cathode ray produces a strong fluorescence or bright light. When an electric field is applied across the cathode ray tube, the cathode ray is attracted by the plate bearing positive charges. Therefore, a cathode ray must consist of negatively charged particles.
So this is how he discovered the electron. Okay, so what he was doing is using this cathode ray tube, and like it just showed, he was using a magnet, and he saw that it was attracted to the positive side and pushed away by the negative side. So that allowed him to discover the negatively charged electron. And he knew it was negatively charged because, again, it was attracted to the positive side of the magnet and repelled by the negative side of the magnet.
We know these negatively charged particles as electrons. A moving charged body behaves like a tiny magnet, and it can interact with an external magnetic field. The electrons are deflected by the magnetic field. As expected, when the direction of the external magnetic field is reversed, the beam of electrons is deflected in the opposite direction. In 1897, J.J. Thomson, an English physicist, determined the charge-to-mass ratio of an electron. He adjusted the electric field so that the electrostatic deflection, theta E, was the same as the magnetic deflection, theta B, and was able to calculate the charge-to-mass ratio of an electron using the following equation.
Don't worry about this equation too much. Just understand that this is some of the deeper science that he was doing, and that he was able to find that basically there's a charge, but there's not very much mass to the electron.
E is the applied electric field, theta is the angle of deflection, B is the applied magnetic field, and L is the distance traveled by the cathode rays. Thomson determined the charge-to-mass ratio of an electron to be negative 1.76 times 10 to the 8th coulombs per gram.
Okay, again, just electrons are incredibly small, and have a negative charge. Okay, that's what we need to take away from that. All right, let me stop that share. New share, back to PowerPoint. Here we go. All right. All right, so while J.J. Thomson discovered that the atoms contain smaller parts, which are now electrons, this is the only thing that we know exists beyond beyond atoms at this point. He did state that the overall charge of the atom was neutral. And he realized this because if you just take a grouping of atoms, right, just as the solid pieces, and you hold it up to a magnet, nothing really happens unless that has some magnetic properties. But for the most part, you're not going to see a result. You're not going to see things being attracted to it or things being repelled to it because the overall charge of the atom is neutral. So obviously, he realized that while there were negative parts, because the overall charge was neutral, there had to be some kind of positive parts to counterbalance that, okay, to balance the negatives and positives. And so he came up with a model of the atom he called the plum, or it got coined the plum pudding model. Now, you don't need to know a lot about plum pudding, but apparently it was all the rage back in the day. It was a nice dessert. And basically it was this kind of bread with little plum pieces baked into it, okay? Now, so basically we need to think about that as his atom. What he stated was that atoms are mostly positively charged material and that they're just negative little particles or bits called electrons located throughout the positive material. Okay, so let me draw you a little example of that. This is gonna be bad. Remember, I'm not an art teacher. Okay, so let's say this is the atom. He basically said this whole part of the atom consists of positively charged material, and in that positively charged material are little negative charges called electrons. Okay, so this was his model of the atom. The idea that most of it's positively charged, but then within that positive material, there's all these negative parts, and that these all cancel each other out to make a net neutral atom, no overall charge. Now, for his work, he made a really big leap, discovering that the atom is not the smallest thing, discovering that the parts of atoms have charges, and so for his work, he did win a Nobel Prize. So he became a pretty famous scientist after he published a lot of his work. Then we get to another gentleman who's actually a buddy or a student, I can't remember, a buddy or student of J.J. Thomson, and his name is Ernest Rutherford, okay? So Ernest Rutherford in 1909 performed a gold foil experiment. And I'm not going to get into what he found because we're going to watch the video, and the video is really going to show us what his discovery was and how he made it. So let me go ahead and play this video. Stop that share. Go back to the class. Open the next video. Share that video. And again, pop in if the sound's not working. Oh, stop. Let me share that screen first before you start yammering. Oh, stop. That's not what I wanted to click. There we go. Share screen. That specific tab. Okay, here we go. Let me start this over. All right. Rutherford experiment, nuclear atom.
In 1910, Rutherford and his co-workers were studying the angles at which alpha particles were scattered as they passed through a thin gold foil. Most of the alpha particles passed through undeflected. However, a few were found to be scattered at large angles. Okay,
so what they're doing is this blue box represents a box that's creating radiation. Okay, they got something in there that's shooting out radiation, alpha particles. And what they're seeing here is they're studying these little alpha particles at a gold leaf a sheet of gold leaf, piece of gold paper, basically. Now, the reason that they did gold leaf was because this is something you can get incredibly thin and it doesn't necessarily break very easily. It still will break, but you can, make it thinner, run it through a press, make it thinner, run it through a press, make it thinner, until you get to only about a couple atoms thick. Not many materials can do that. So it was actually really incredibly smart that they used gold because you can get it incredibly thin, and that just allowed for this gold leaf to be a couple atoms thick. Now, as that radiation passed through that gold foil, what they found is that most of it most of it hit the back. And what this is this is kind of like a photographic plate, okay? Or film almost, if you will. And what they're seeing here is anytime the radiation hits the film, it's gonna cause a spot to occur, right? And what they're seeing is that most of the time it passes straight through the gold foil and hits this film right here directly in line with the box of radiation. However, sometimes they would get deflected to other angles. And so this is going to lead him to his major idea. Let's find out.
Some even back in the direction from which they had come. This meant that they had collided with an object much more massive than the alpha particles themselves, yet so small that only a few alpha particles encountered them. This atomic level view shows what is happening. Most of the atom is occupied by the low mass electrons. The nucleus is small and massive. When an alpha particle encounters a nucleus, it is scattered at a large angle.
Okay, I'm going to go back to that just for a moment, okay, because this is really showing us what was happening in this experiment. Now, obviously, the alpha particles did not follow one straight path, right? There's some little bit of variation where they're coming through. And so what happens is Rutherford realizes that atoms are actually mostly empty space, that most of the atom is just the region where the electrons exist, and there's a very small core with a pretty big mass. And that's what was happening. Most of the time, the atoms would just pass through here, not hit any of the cores, and therefore hit the back of the photographic plate where he expected to see it. But every once in a while, when they hit these cores, they would get deflected. So sometimes they would deflect one way, sometimes they would deflect the other way, or if they make really good contact, they would deflect straight back at the radiation box. So this was really, really important in his understanding that the atom is actually not solid. This is a huge deviation because remember, up until now, atoms are solid, atoms are solid, atoms are small, right? Indivisible, indestructible, solid pieces of matter. But now Rutherford is saying, whoa, hold on a minute. Atoms are not quite as solid as we thought. There's actually a lot of space here, okay? So that was his gold foil experiment. Stop that share, and we're gonna go back to the PowerPoint. Share screen, PowerPoint, please. Okay. All right, so again, Ernest Rutherford realized that the atom consists of a small core or nucleus that contains most of the mass, but this nucleus is made up of the positive particles, so we called them protons at this point. So pro-positive protons, positive charge, electrons, negative charge. And he said the protons are surrounded by the negatively charged electrons, but actually most of the atom is empty space. Please underline that. That is so important. Most of the atom is just empty space. That is super important for how atoms are going to interact and work with each other, okay? Atom is actually just mostly empty space, very little solid mass. Excuse me. Now, Ernest Rutherford was obviously working with a lot of radioactive stuff. He did a lot of work with radioactivity, alpha and beta particles, gamma rays, and waves. And he's referred to as the father of nuclear physics. And for his work, he won a Nobel Prize. And guess what? He was actually a student of J.J. Thomson. So remember, J.J. Thomson's the plum pudding model. So remember, J.J. Thomson was the last guy to kind of say, hey, the atom is a solid, positive chunk of material with all these negative parts. And then Rutherford comes, he learns from him, and he goes, you know what? Teach, you're actually kind of wrong. The atom is actually mostly empty space. And I can prove it to you with this experiment, the gold foil experiment. Any questions about Rutherford before we move on? All right. After Rutherford, we get to a Bohr of a person. No, I'm just kidding. His name is Niels Bohr. He looks like he might be a little boring. I don't know. But Niels Bohr, in 1913, he proposed the Bohr model. Okay, so he's expanding upon this model. So he took Rutherford's model and changed a little bit. He suggested that the electrons actually travel around the nucleus of the atom in orbits or definite paths. So if you think about how the planets orbit the sun, he's kind of saying that electrons do a very similar thing on the atomic level, that they orbit the nucleus. But he went a little bit further and he explained that electrons can actually jump from one level to another depending on their energy. So that means when you heat something, it's going to gain energy and it's going to jump up to a higher energy level. So let me draw you a little picture. Again, please don't judge. Okay. So let me draw this. So we got a small core, right? There's my nucleus. And he basically said the electrons go around in definite paths or orbits. Okay. Now I'm going to tell you, this is not the correct model of the atom, but this is a pretty good way to think about the atom. And we're actually going to be using the Niels Bohr model a lot. So basically these electrons are going around, traveling around the nucleus of the atom. He realized that these different levels represented different forms of energy. So what you can do is when you add heat to something, you excite the electrons, you give it energy, the electrons get real excited, and one can jump one or more levels up. Now it's not supposed to be there, so eventually once that energy leaves, it's going to fall. Okay, it's going to fall back down to where it's supposed to be. And here's the cool thing. We know that because of potential and kinetic energy, if it's further away from the nucleus, it has more potential energy. As it falls back, it can't just lose that energy, right? Energy cannot be created or destroyed. So this is actually explaining why things glow when they are heated. When that electron falls back down to its normal spot, it has to give off some of that energy, and it does it in light. And how far the fall is, or which energy level it's jumping from and back to, is actually going to determine what color light is given off. So this is why if you've ever had like an electric stove or something like that, you turn it on, electricity starts traveling through that coil. What happens to that coil? It starts to glow orange, doesn't it? The lights in my room right now, they're just tubes of gas, all right? That gas is not bright in any way until you pass electricity through it, and then all of a sudden you excite the electrons and they start to glow. So again, this is what's happening, and this is Niels Bohr really explained why things give off light when they're heated or when they gain energy. Now, for his work, he did win a Nobel Prize. And he was a very close colleague to Ernest Rutherford. So he and Rutherford were kind of working together. So remember, Rutherford found that the atom is mostly empty space. And he's kind of going one step further and saying around that empty space, the electrons orbit the nucleus. Then we get to Erwin Schrödinger, made more popular by some online memes and stuff like that about, you may have heard of Schrödinger's cat before. It's just the idea that if something is in a state of being unknown, it's both like true and false, alive or dead. So basically, if we had a cat in a box, until we open the box, the cat could exist in one of two states. The cat could either be alive or the cat could be dead. And so the cat is both alive and dead until we open the box and find out. But that's not why we're talking about him today. We're talking about him because he also added to the idea of the atom. In 1926, he further explained the nature of electrons by saying, you know what? We cannot know the exact location of an electron. Basically, what he realized is when we do the math to figure out where the electrons are, we can either know one of two things: where their location is at a given moment, or what direction they're traveling or what speed they're traveling. We cannot know all of that information at the same time. So he said, we cannot know the exact location of electrons. So what he said went a little bit further. He said, therefore, a more accurate view of the electron is called, where the electrons exist, is called the electron cloud. So just around the nucleus, because he's kind of deviating from Niels Bohr, he's getting away from what Bohr said. Bohr said the electrons follow these set orbits, right? Well, Schrödinger is saying actually they don't follow set orbits. We can't know exactly where they are, and just we call this area where we're likely to find them. He coined it the electron cloud. He just said there's a region of space where it's likely to be found. So again, if we had the nucleus here, he would just say, well, around the nucleus is this area, and this is where the electrons, which are you'll see me mark as E minus. That's a little shorthand for electron. Electrons are likely to be somewhere in this region. Okay, but he said we cannot know the exact location of the electrons. And for his work, he won a Nobel Prize. All right, after Schrödinger, we get to James Chadwick. Here's James Chadwick. Now, James Chadwick realized that when he was looking at the atomic masses of most elements, they were most of the time double the number of protons. So if an atom had 6 protons, a lot of times its mass was 12. If an atom had 7 protons, a lot of times the mass was 14. And so that led him to the discovery there must be another component, another particle in there that has mass. And that led to the discovery of the neutron. Now, neutrons have no charge. They are neutral. Neutral, neutron, neutral. Okay? The reason that it took so long to discover the neutron is because it wasn't interacting with a lot of the experiments. It wasn't interacting with a magnetic field or anything like that. So it was harder to detect. And it wasn't until he realized that the mass was double that he realized that the neutron was there. There was something else in the core. Now, James Chadwick worked on the Manhattan Project. Does anyone happen to know what the Manhattan Project developed? Yeah, nuclear weaponry, okay? This is one example where science is not always used to better humanity. Science can also be used very dangerously to create weapons of mass destruction, like atomic bombs. So the Manhattan Project created the atomic bombs that we dropped on Japan, Hiroshima and Nagasaki. So he worked with Ernest Rutherford. So again, you see a lot of these guys working at the same time. So this was kind of a real rapid succession on discovering the different parts of the atom and how they worked. And for his work, he also won a Nobel Prize. So if we look at this and we go through the progression of the atom, we started all the way back with Democritus and John Dalton. Remember, they said that the atom cannot be small, indivisible, indestructible, cannot be created, cannot be destroyed. Boom, there's their model of the atom, the Lego model. Then we get to J.J. Thomson, and J.J. Thomson says, you know what, actually that is not the smallest division. There are these positive parts and negative parts. The atom is mostly positive with little negative bits. This is the plum pudding model. Then we move forward, and Rutherford comes along and says, you know what, it's actually not solid at all. It's mostly empty space, and I proved that with my gold foil experiment. There's a small core where the protons exist, and the electrons are just outside the nucleus. And then Bohr came along and said, actually, they are outside the nucleus, but those electrons follow set orbits or paths. So we can kind of see that here. And then, you know, Schrödinger had to come along and say, actually, Neil, we don't know exactly where they are. We just know they're in this region. So let's just call it the electron cloud. So that kind of updated the model of the atom again. And then last but not least, we have Chadwick coming in. And Chadwick is saying, you know what, the mass is double. There must be some other particles. And so he added the neutrons into the nucleus. And if we look at this on a timeline, we can see that not a lot happened until, you know, the 1700s, 1800s, and then things happened very, very, very quickly. Okay. Any questions about the history of the atom? All right, so now let's switch over. It's just the next page, I think, for you guys, and we'll take a look at the practice for today. So share my screen again. Screen 2, there we go. Here's the classwork. So we're going to go ahead and open Brave the Elements. Brave the Elements. And I got one more little YouTube for you. Let's go ahead and listen to this. As a little pre.
Well, life on the farm is kind of laid back, ain't much an old country boy like you can't.
Stupid advertisements. Advertisements everywhere. All right. But what we're going to be doing, if you take a look at the very top, okay, of the paper, we're going to be taking a look at what these are and making a prediction about what these things have in common. So let me switch that back over. So if you see here, Brave the Elements, there it is. We're taking a look. We're going to listen to the song, and then we're going to predict what the words in the song have in common. And if you can, support your ideas with prior knowledge and stuff like that. All right, so let's take a look. I need to do a different share, of course. So give me just a moment to navigate all of this wonderful BS. Yeah, that's fine. Share, please. Where did it go? That's not the one. Did I accidentally close it? No, I did. Oh, I see. Okay, let's go there. Go back here. Please share the screen that I want you to share. There we go. All right, sound should be shared, so we should be good to go. If it's not making sound, please just let me know.
And now, ASAP Science presents the elements of the periodic table.
There's hydrogen and helium, then lithium, beryllium, boron, carbon everywhere, nitrogen all through the air, with oxygen so you can breathe, and fluorine for your pretty teeth, neon to light up the sign, sodium for salty times,
Magnesium,
aluminium, silicon,
phosphorus,
then sulfur, chlorine, then argon,
potassium,
and calcium so you'll grow strong,
scandium,
titanium, vanadium, and chromium, and manganese. This is the periodic table, noble gas is stable, halogens and alkali react aggressively. Each period will see new outer shells while electrons are added, moving to the right. Iron is the 26th, then cobalt, nickel coins you get, copper, zinc, and gallium, germanium, and arsenic, selenium, and bromine film, while krypton helps light up your room, rubidium, and strontium, then yttrium, zirconium,
niobium,
molybdenum, technetium,
ruthenium,
rhodium, palladium,
silverware,
then cadmium and indium,
tin cans,
antimony, then tellurium, and iodine, and xenon, and then cesium, and barium is 56, and this is where the table splits, where lanthanides have just begun, lanthanum, cerium, and praseodymium. Neodymium's next to promethium, then 62, samarium, europium, gadolinium, and terbium, dysprosium, holmium, erbium, thulium, ytterbium, lutetium, hafnium, tantalum, tungsten, then we're on to rhenium, osmium, and iridium, platinum, gold to make you rich till you grow old, mercury to tell you when it's really cold, thallium, and lead, then bismuth for your tummy,
polonium,
astatine would not be yummy,
radon,
francium will last a little time,
radium,
then actinides at 89. This is the periodic table, noble gas is stable, halogens and alkali react aggressively. Each period will see new outer shells while electrons are to the right. Actinium, thorium, protactinium, uranium, neptunium, plutonium, americium, curium, berkelium, californium, isonium, fermium, and olivium, nobelium, lawrencium, rutherfordium, wm, supercium, boreum, hesium, lignanium, dubsinium, mercenium, copernicium, nihonium, flerovium, moscovium, livermorium, tennessine, and organesson, and then we're done. Thank you guys so much for watching.
All right. So that, what do you guys think? What do those things have in common? It's a prediction. What do you guys think these have in common? Don't all shout at once. Nick, we turned off our computers and stopped listening half an hour ago when you were talking about the atom. We have no idea. Anybody? Anybody there? Hello?
Sorry, my phone's acting up.
That's all good. So what do we think? What do we think that has to do? What do those things have in common? They might be all the different forms of what? What are we talking about today? Atoms. Yes, we're talking about atoms today. So what we saw was a periodic table of elements song. And what I really like about that is, yeah, it is a little cheesy and catchy, but The key is that it gives you an example of where these atoms exist, you know, in everyday life. So I kind of like that it puts kind of a picture with the name so that you can at least kind of see where these things are used or where you might encounter them. But the key is that all these different things are the different kinds of elements. So that's what we're taking a look at. Oops, that's not what I wanted to do. Share screen, screen 2, thank you. All right, so looking back at the Brave the Elements. So what do they all have an idea in common? These are all the different types of atoms. So I'm gonna allow you guys, holy cow, that did not come out. Don't worry about this one. But I'm gonna allow you guys to go on ahead and work through this on your own. What you're gonna do is it's just like kind of a little read along. You're gonna answer some questions, you're gonna read along, you're gonna make a little picture, you're gonna read along, you're gonna fill out this chart, and then make a more updated picture, and then there's a little flow table for the different parts of the atom. So it really should not take you very long. I'm not gonna walk you through this because it's very straightforward. Go ahead, read the section, answer the questions, read the section, do a little brainstorming, and then make a little prediction picture. Then read this one. This elements and atoms section, this is the most important one in this chart. So please spend some time on this because we may actually even go over this tomorrow before I collect it because I really want you to have this chart correctly filled out. So for the chart, you're going to tell me what charge it has, if it has a charge, so it can be positive, negative, neutral, or no charge, and then where it is in the atom. So basically that's going to be 2 places. Is it in the nucleus or is it in the electron cloud? Those are going to be the only 2 places, okay? And then do your best for number 10. This, after we get through the section, you should have a good idea for where stuff is and what the drawing might look like. And then do your best to fill out the little flow chart. What questions do you guys have for me? All right, I don't hear any questions. So after you're done with this, guys, do flip over to the exit ticket. There's a little Google form there. Go ahead and answer that exit ticket once you're done with the practice and submit that as well. So I will collect the practice tomorrow in class, but do go ahead and submit the exit ticket after you're done with the practice today. And if there's nothing further, guys, thank you for zooming in today and learning about the history of the atom. It's going to be a great help for you moving forward as we continue to talk about the periodic table of elements and how these things are going to be built. We're going to look at a closer look at the structure of the atom as we move forward. Tomorrow, we're going to focus a lot more on the periodic table, the patterns on the periodic table, all the information that it contains. And then next week, we're going to get into the structure of the atom, and then we're going to start talking about how they bond and join together. Okay? But otherwise, guys, again, thank you for zooming in today. And if I don't see you before then, I'll see you tomorrow. Hang on, I can't hear you. What was the question? I mean, yeah, but why wouldn't you just knock it out now, right? Because if you go upstairs and move forward, you're gonna get distracted and it's not gonna get done. Then you'd be like, Nick, I meant to finish this and then I forgot to. So you're here, you might as well finish it while you're here. I mean, if you want to go upstairs, as long as you work on it, it's fine. I'll let you go upstairs and work on it, but it does need to be completed. Okay.